Oh, yeah, Harshal, we can hear you.
So can you see my screen?
Oh, it's loading. Yeah, now I'm able to see your screen. Okay.
So actually, sir, during the simulation, it was showing some errors.
Okay.
Actually,
Can you go?
I
Mhm.
rectified those errors, like I removed the materials and a
Okay.
mesh wasn't generated on the top cap, so I tried to regenerate it.
Hmm. So were you able to do the simulation then, or you still
Uh,
have?
no, actually, I was having my lunch, so I didn't.
Oh, okay, no problem. So if you remember the process, maybe you can try it out from your end. If still you're facing any issues, you can again post it on the community, and I can help you out there. So do you
Sure,
want
sir.
my
If
help?
I have
Or?
any query, I'll definitely post it.
Sure, no problem. So you can replicate the process which we had done earlier. So if there's any issue that you have, then you can post it and I can help you out on the community itself.
Okay, sure, sir.
Sure, sure then. So yeah, I think we can start with the session. Dharmendra, could you make me the presenter again? Yeah, okay. So I'll just start sharing my screen and we can start in a minute or so.
Now you can. You are now presenting.
Right, right. Okay. Is my screen visible?
Yes.
Okay. Okay. How many participants do we have? We have about 73. Do you want me to wait for a
Right
while
now,
or?
there are 79, but
Okay.
maybe in a while everyone can join.
So do you want me to start with the session or do we wait
Yeah,
for
yeah.
the
Please,
others to
please
join?
continue.
Okay, sure. So we'll start with the session then. So in this session, what we'll be mainly discussing is a tool which is DYMOLA. So I'm not sure how many of you have heard about DYMOLA, but DYMOLA is basically a 1D simulation tool wherein you can actually design physical systems using the model-based systems engineering approach, wherein you actually don't model it in terms of like you do it in CATIA or the Simulia apps. You basically drag and drop these physical components from your main libraries and you can directly start working on them. So I'll take you through it. You'll be able to, towards the end of the session, you'll have a much more better understanding about how to use DYMOLA and what DYMOLA actually does basically. So coming on to the agenda for this session, so what we'll be mainly talking about is the Modelica standard library. So DYMOLA is based upon a standard library of components that it gets. So the standard library is basically the Modelica standard library, and the how these components are built are using the Modelica language. The next we'll be doing a basic of the DYMOLA UI and everything. Then we'll be simulating a basic model, which is an example in DYMOLA, which is an industrial robot model. And then we'll be creating our own model for a DC motor. So we'll actually drag and drop components from the library which we have, and then we'll be creating our DC motor. And then we'll be creating a fluid model. So fluid circuit model we'll be creating by dragging and dropping the fluid components. So that is how we'll be going through this session. So starting with what is Modelica and what is the Modelica standard library? So Modelica is basically a non-proprietary object-oriented and equation-based language. So Modelica in itself is a language and it is similar to a lot of object-oriented languages out there like Java and C++. But the difference here is you actually write a code in order to build a model. So it's not for executing a given set of codes, it's to build a model. So how the Modelica standard library is basically, it consists of a standard set of packages. So you have the electrical package, you have the mechanics package, you have the magnetic package, you have the thermal package, the fluid package, mechanics, and state graph. So what this basically means is individually each of these packages have a set of consist of a set of components. So for example, if it's your electrical package, you will have a set of components from the electrical and electronic side. For the hydraulic circuits, you will have a lot of hydraulic components such as pumps, you'll have your vessels, you'll have your valves, temperature sensors, and all of this. For mechanics, you'll have your gearbox, Then you'll have your inertia, you'll have your spring models and all of these. So how do we combine it and use is what we'll be looking at further in the session. So on the image on the left side is basically the Modelica standard library. So these are the packages which it consists of: the blocks, state graph, electrical, magnetic, mechanics, fluid, media, and there are multiple libraries like that. And again, Modelica is not owned by anyone, so it's basically free. So it's basically the library is free, and once you buy DYMOLA, it comes with DYMOLA itself. So the library which you're going to get with DYMOLA is the Modelica standard library, and it consists of a few of these packages like we discussed. And using those packages, you can build quite a lot of models. That is your physical system models you can build through it. And Modelica is run by a non-profit organization called Modelica Association. So they are the ones who handle and add new components or add a few changes in the existing libraries itself. So coming on to a detailed view about what these libraries are and what all components they consist of. So we'll be starting with the electrical library, the electrical package. So as you can see, the electrical package is further subdivided into three different packages. So it has analog, digital, and machines. So what this is basically is your analog package will have all the electric and electronic components, such as the resistor, capacitor, transformers, diodes, transistors, and switches and sources and sensors. These are the components which you can picked from the analog package of the electrical package. Similarly, the digital one, you will have all the digital electronic components that you require in order to build a physical system. So these will have all your logic gates, your delays, your gates, sources, the converters, and all of that is present in this particular package. Then you have machines. So machines is basically wherein you will have the DC motors, you'll have transformers, you will have EMFs. So all of these are already pre-built components which you can directly use. So it's mainly giving in a few values for it and then simulating your model is what DYMOLA is mainly used for. Then what you have is the mechanical package. So the mechanical package consists of the translational, rotational, and multi-body packages. It's further divided into them, where the translational will have all the translational components such as sliding mass, your spring and damper systems, while rotational will have all your gears, planetary gears, your brakes, your clutches. All of these type of components are present in your rotational package. While in multi-body, it's basically present of three-dimensional mechanical systems that consist of joints, bodies, your forces and sensors, and all of those type of components. So you'll be actually building models, and you might get to know more about it towards the once we continue with the session. Then you have the fluid library. So fluid library is basically used for building one-dimensional fluid flow circuits. So it consists of a lot of components such as vessels, pipes, and fluids. So what you can do is you can drag and drop these components, build a circuit out of it, connect them, and you can actually simulate pipe flows. You can go through and actually build a pump model out of it. So there's a lot you can do with these fluid libraries too. Now there is a media library. So the media library is something which is basically the medium that will flow through the given components. So the media library the media library can be used with the fluid library in order to generate these fluid flow simulations that we have. Then we have blocks. So the blocks basically consist of a lot of input and output blocks, such as sources. You have the different delay components, you have the PID controllers, and a lot of components like those are present. And the thermal library is basically for the fluid heat flow and heat transfer components you'll have. So you'll have components like pipes, pumps, valves, ambient sensors. You'll have sources. You can heat a given pipe through a given input. So a lot can be done towards the heat flow and heat transfer packages. So this is how the DYMOLA UI looks like on the platform. So you will have your main modeling window wherein you'll be creating a model using the components from the DYMOLA library. So the modeling window will be something like this, while the simulation window will be used to plot all your graphs. So all your variables that you have that you'll be finally simulating in the end will be plotted in the simulation part of the DYMOLA. So on platform, DYMOLA is called as behavior modeling. It's not called as DYMOLA, but a standalone version, that is the software of DYMOLA on itself, is called as DYMOLA, but on platform it's called as behavior modeling. Now further, the window can be divided into, you have the DYMOLA main window, which consists of all of them. Then you have the edit window, which will be basically the place where you'll be creating the models and you're dragging and dropping your components and building these circuits. While the component browser will consist of the components that your given model is made out of. So for example, if you have a model that consists of a lot of components from various libraries, then in that case, you can further easily view them in your component browser. While your package browser will show you all the components that a package consists of. And that's how it is basically divided into. So you have your package browser, component browser, and edit window. So coming on to the package browser, so if you can see the image on the left side, it's basically the components library. So for example, if you enter the mechanics and multi-body, you can see there's a lot of examples, a lot of components that it consists of. So that is what the components library is. While and the components are dragged from there and dropped onto the main edit window, and you can create a circuit model as it is shown in the picture. So the image basically depicts a motor model, so wherein you're testing a motor model using a feedback and you're assigning a gearbox to a model. So if you have an electric DC motor to which a gearbox is attached, and then it's further connected to a load, which is an inertial load. So that's how you can actually model the physical systems. So your component browsers, the component browser in itself is very helpful, mainly because usually components on DYMOLA are built out of quite complex components. So they consist of a lot of components in a series of connections. So to go and understand where a component is located, it's quite hard. That is where your component library comes in and helps you. The component library, so for if you click on the one single component, it will display the components that that particular model is made out of. So that could be very helpful if you're working on models which have a lot of components used in them. Again, the component browser helps in a better representation, and also if you're working on a given model and if you want to go and enter a given component, you can use the component browser to do that. You can just go double click on that component and enter the edit window for it. So now one more thing that we need to know is in DYMOLA, there are multiple layers basically. So you have something called as an icon layer. You have something called as a diagram layer, documentation layer, Modelica text layer, and use classes layer. Okay. So coming on to what an icon layer is. So icon layer is basically the display of a component. So it's not something which is related to the modeling of it. It's just a display. So if you drag and drop a component, how does it look when you drag and drop it? So if you can see the images, the model which is built, so there are multiple components that are there, right? So if there's a gearbox, so the gearbox is a diagram of the given component. So that's what is done in the icon layer. While the diagram layer is basically your model itself, so on which you will be actually working. So by default, you will be on the diagram layer. And documentation layer. So in Modelica, to help the users understand more, there's something called as documentation layer. Once you open it, you'll have a complete documentation of how this model can be used, what all components this model consists of, and how do you actually fill in the data for the given variables that are present there. So that's what the documentation layer is for. And as I told you, that Modelica text layer is something which consists of all the code. So since Modelica is basically a language, and using this language you can build models. So in that case, the Modelica text layer will contain all the code in order to build these models. This is what the Modelica text layer is basically. And the used classes layer is basically you have multiple classes in Modelica. That is your the multiple packages that you have. So the different packages that you use will be shown in your used classes layer. So that's how it's basically divided: icon layer, diagram layer, documentation layer, Modelica text layer, and use classes. So you can switch between them using option on your window itself. So I'll be showing you that too. Using that option, you can switch between each of these layers and then work on them itself. So once you're done with the modeling part, you enter into the simulation mode. So simulation mode is something where you simulate the given model to basically have it with the variables, and you can plot your graph, you can plot the different variables, you can plot different graphs with respect to different coordinates. So a lot can be done. And then your animation window is basically where you can animate your given model. So for example, if you have designed a physical system, here in this case it's a robot model. So this robot models need to be simulated too in order for how do they actually work. So for that, you'll be using the animation tool, wherein you can play the animation and see as to how the robot functions when you do a given action to it. So now that we have a basic info about what DYMOLA is, what we'll be doing now is we'll actually shift to the tool and directly start using it and understand more about it on the hands-on session itself. So DYMOLA is something, if I'll try to explain more about it, it'll be a little bit confusing for the user too. So what we'll do is we'll actually shift to the hands-on session and I'll directly show it on the tool itself of how to use it. So in the meantime, if anybody has any doubts, they can put it on the chat box and I can help you with that. If you want to know anything more about it, just give me a second. Just give me a second. I'll just start sharing my screen here. Hello, Dharmendra. Can you confirm if I'm audible?
Yes, that you're audible.
I'm audible, right? Okay, sure. So I'll just present my screen. Yeah. Yeah. So what you'll have to do now is you can go onto your platform and you'll have to open. So you have a role which is for the. One second, just a delay happening. So you can go onto your platform and there is a role which you have called systems engineer. So systems engineer role is basically for using the behavior modeling and behavior experience tools. So you'll have to open behavior modeling on your platform. So what you can do is you can go onto a new tab and you can just search for behavior modeling in here. You just have to search behavior modeling and you can open the tool too. So I hope all of you were able to do it. I'll just repeat once again. You'll have to just go onto your 3D compass and search for behavior. So you can just write BEH and you'll have your behavior modeling tool. So you don't have to go to behavior experience. That's a different topic altogether. So we'll be working on behavior modeling itself right now. So, okay. So this is how your behavior modeling will look like. This is how the UI for the platform will look. Now what you'll have to do is you'll have to import a Modelica library now. So how do you do that is, I'll come to that, but before I'll just explain you a bit about the UI itself. So you have your package browser, which is being displayed here. Then these different layers which you have is the parameter and variable editor. Then you have your component browser. So if you have a model here, you can actually see the components that the model is made out of. And then you have the Modelica library. So this is a normal specification tree. So what we'll be mainly on is the package browser. Now, if you see the action bar, make sure that you have the display icons option set up. So to do that, you'll just have to do right click and select the display icons and text. So you have behavior authoring. So a behavior authoring is a place from where you can see the documentation layer of a component. You can see the class attributes. You can add a new class. You can add a new package. So this is what is done using the behavior authoring tool. While on the other hand, behavior tools is where you actually import libraries. So at this point, the first library which I'll be needing is the Modelica standard library. So to do this, what you'll have to do is you can go here and select Modelica standard library. So once you select it, it'll, so for the ones for whom it's already being shown, you can directly open the Modelica library, but for the ones who the package browser is empty, you will have to import it using this way. But if this method does not work, then I'll show you one more method of how to actually import these libraries. So right now it's asking that the Modelica 4.0 library is not in the database, and the 3DXML containing library has been found in my installation directories. So now I'll have to import the Modelica 4.0.0 library to my platform right now. So I can just click OK. So the option where I got it from was you'll have to go to Behavior Tools, and there is an option here which you can see is something which looks something like this. And you'll have to open the first one, which is Modelica Standard Library. So you can just click on it and enter OK. And then the system will try to fetch it through the installation and import the library to your platform itself. But this method might not work for some, and I guess it will show an error for me too. So okay, so it is showing an error importing a data briefcase. So on the chat box, could you confirm if you are encountering the same error? The students, if you're trying to import the library. Okay. Okay, no problem. Lloyd, sir, I just need one help from your end.
Yes, Siddharth.
Yeah. So the installation directories for these students, that is the B423 cloud, where is it located for them?
If they have installed it will be on the C drive only.
C drive itself, right?
So
Okay,
it's the
no
same
problem.
procedure, just that the tenant will be different.
Right, right. No problem. So I'll give them the other way how to do it. Okay.
Sure.
So you can just follow the procedure which I'm doing. So right now, what you'll have to do is you'll have to import a new content. So you'll have to go and import. Okay. So plus icon and import. And now if you, so it needs to be a 3D XML file on your disk, and we'll search the given file right now. So you can set this option. And right now, what you could do is you could either go for the C drive or the E drive on where you have installed your platform. So for me, it is on E drive. So you'll have a folder named B423 Cloud on your system. So you could just check in your C drive or E drive, it should be located there. So I'll just check my chat box simultaneously if you have found it or not. So for the ones who haven't found it, can just put it there. And the ones who have, yeah. So I see Himanshu has confirmed. Could the rest also just tell if they have found the library or not, or found the B423 cloud folder? Okay, so you have found it, right? So once you enter the B423 cloud, so just follow it step by step. The next folder, once you enter the B423 cloud folder, you will have WinB64. So you'll have to enter the WinB64 folder here, and you'll have a lot of options here now. But where we need to go is into, resources. So just scroll down a little and just enter resources. So it's B423 cloud, WinB64, and then you'll have to enter resources. Okay. So once you enter resources, you'll have to go into one more folder. So just scroll down a little and you'll find something called as DBM libraries. So if anybody has missed out on any steps, don't worry, I'll replay the whole process and you can follow it then. So once you're inside resources, you'll have to go into DBM libraries. So once you're inside DBM libraries, there'll be two folders now, 3DXML data and documentation. We need to go into 3DXML data. You can open it and you'll see there's a lot of 3DXML files that are present here. So these files are basically your different set of libraries. So we have a battery library, we have a brushless DC library,
We have piping libraries. There's a lot of libraries that are present here. But what we require right now is the Modelica standard library. So you'll just have to scroll down a little and you can directly go into the M. So you'll have something called as, so you'll have two Modelica standard libraries. So one is 323 and the 323 and the other is 400. So basically it's two different versions of the library, and what we'll be requiring is the 400. Okay. So for the ones who have been able to locate it, you can just click on it and select open and it will select. Now make sure you're importing this as a new. So as a new, just make sure you have a duplicate string given to it and make sure it's unique. Because if there's the same instances of these libraries are present, then again you will get a data briefcase error. So it needs to be a unique library. So just make sure you're given a different initial or just given something that is related with your name or just your name itself. Okay, so and then you can press OK and then your library will get imported. I'll just replay the process for the ones who didn't follow. I'll quickly go back. Okay, so coming on to where my installation is, it's in drive E. So I'll have to go enter the B423 cloud. So once I'm in B423 cloud, then I'll have to enter WinB64. There's only 5 folders here, out of which you'll have to enter WinB64. Once you're inside WinB64, you can just scroll down a little and you will find a folder named resources. So all you have to do is just open it. And once you're inside the folder, the next thing which you have to do is just scroll down and try to find DBM library. So it's basically the DYMOLA behavior modeling libraries which we need. And you'll find it here, which is DBM libraries. Just double click it and open it and go into 3DXML data, scroll down a little and you will find the Modelica standard library. And the version which we require is 4.0.0. So just make sure you've selected the right version of the library and then you can enter open and make sure you give a unique duplicate string value. Just enter anything with related to your name and that should be enough and just press OK. So then the import process will be going on. So if anybody has any doubts or they haven't followed the process, you can put it on the chat box. I'll quickly repeat the process again. Okay, so Shashank, do you want me to repeat the process now or have you got it? Okay, that's good. Anybody else who's facing any issues that they want to clarify, I can replicate the step for you. Okay, so now if you can see, I have the library imported now, so I can just press OK. And now if I use this command, it should open my library, else I'll search it from the 3D search itself. Okay, so once you have imported the library, you can press OK, go on to behavior tools, and then use the same command and press on the library. Now, since it's already present in your database, it will load the given session. So the ones who are done till this step can just confirm on the chat box once, so that for the ones who haven't, I can show them the process again. Okay, so I hope everybody was able to do it. Yeah, even the one which Mihir put, you can use that same and you can import the libraries. Okay, so once you have the library, now we can go further and try to understand how these components work. So what you can do is you can open this drop down of Modelica. Yeah, you can open the drop down of Modelica and you will see there are multiple packages that it consists of. So it has blocks, complex box, clocked, state graph, electrical, magnetic. So there's multiple libraries, and all of them are used in order to build a certain component. Now what we'll be mainly going into is the mechanics library. So it's just, I think, like 6 to 7 packages below. There's a mechanics library, and you'll have to enter multi-body and examples. Okay, so I'll just repeat it again. So you'll have to go into mechanics. In mechanics, you'll have 3 different packages. So you'll have to enter multi-body. And inside multi-body, you'll have an option for examples. So one good thing about Modelica is every standard package that you have comes with an example. So in case you want to try and understand what these packages can be used for and what components can be made out of them, this particular these examples would be really helpful on how to connect these components and how you can build components out of it. So you can just maximize the examples and go into systems. So in systems, you'll have something called as robot R3. So once you open that, you'll have a full robot option here. And you can just double click it. Okay, I'll repeat it again. It's in mechanics, multi-body, examples, and in examples, you'll have to go into systems and robot R3, and then you have a full robot example there. So this is the procedure which you will have to follow in order to have the robot model accessible to you. Okay, so if everybody has done till here, I'll give it about a minute and then we can start with the explanation about this product itself. Okay, so moving forward, so right now I'll just give you an explanation of how this component is built and what all components it has used. So now if you see, we have a whole robot model, and to understand the model, because at this point it's quite vague, there's like multiple accesses here, there's one robot image, so it's quite confusing. So what you can do is you can just right click on your full robot and go into document editor. So just right click on your full robot and go into document editor. So what this gives is basically the document layer which we initially spoke about. And if you expand it, it will give a little bit information about what this example is and what it is built out of and what all components it is using and what all data that needs to be given as an input. So this is what the documentation layer consists of. So it consists of a detailed explanation of the components and of the given example itself. So in this case, it is a 6 degree of freedom robot with path planning and controllers and motors present in it. Okay, so now we'll go inside the components and see how they're built out of. So now what you can do is you can click on the robot image, which you can see. Just right click on it and you can go into show component instance. So once you click on that, it will take some time to load and then you'll be able to see the components out of which this model is built out of. So you can press the center button of your mouse and then zoom in. Center button and right click and then zoom into your given model. Or you can use control and your center button. So it's up to you. Any method that is convenient for you, you can use it in order to scroll through the model itself. So what, yeah. So this robot model is made out of a lot of components that consists of, for example, the body shape is basically how the robot looks like. So they've made it using different body shape, different joints that are defined. So there's a revolute joint that is defined. So there's a lot that is going on at the back end for the model. And further, now if you want to go back to your model, initial model itself, so on the tree, you can see there is an option for previous class. On the top, there are 2 arrows. One is towards the left and one is towards the right. And one is the parent class, which will take you towards the final parent class itself. So what we'll be using is the left icon. So you can just press on it and it will take you back to your original robot model itself. So this is how the this particular component of the robot model as well. Now, each of these axes, how they are built, we'll just take a look at that too. So in the similar way, you can view these components, but in this case, we'll use a different method to view it. So instead of right click and go and show component instance, there's a small bunch of shortcuts which you could use. One, if you can see, this is edit Modelica parameters. You have show component instance again here. So all you can do is just press on it and it will show you the component instance. So the axis which we just saw is made up of a controller, a motor, a gear. It also has three different sensors, one being the angle sensor, the other is the speed sensor, and the other is acceleration sensor. And then further, if you want to understand what these components are made, you can again go into show component instance for the motor, and it will take you to the whole detailed circuit out of which the motor is made out of. So the motor which you see here, it's built out of a bunch of resistors, capacitors, controllers. You have a lot of inductors. You have quite a few components. You have an inertia component as well. You have an EMF. You have a lot of sensors inside it. So this is how a motor component is built. So this component is quite complex. Now to shorten this process, earlier what had spoken about the component browser is where this comes into play. So for example, if you go click on motor and you enter the component browser, you can see all of the components that the given model consists of. So this is where you could use the component browser. So instead of going and searching for a given component, you can use the component browser in order to view what the given model is made out of. So I'm sure right now you might have a little bit of idea of what DYMOLA is. A little bit of picture might be forming as to what DYMOLA is. So it's basically building physical systems out of components from a Modelica standard library. So for example, like we discussed about the motor model right now, it's built out of, so if I'll go again inside it, so this motor model which you can see is built out of quite a few resistors or quite a few conductors, and all of this in a certain logic they are connected and they're acting in sync in order to replicate the behavior of a motor model. So this is what DYMOLA is used for. There can be a lot more complex models that you could build, but this is one of them. Like for example, if you enter the gearbox basically has a bearing and the gear itself. If you enter the gear, there's actually nothing. Gear is like the base class itself. So you'll have gear and the bearing forming the gearbox. So now what we'll do is, after understanding this, what we can do is we can actually simulate this model. So since it's an example, the simulation setup is already built up for this. All you have to hit is simulate, and then we can see that the simulation takes place. So in this model, what we'll also have is actually a physical model that is created using the mechanics multi-body library components. So using that, a physical model is also created. So once the simulation goes through, you will see a model that appears in the background as well. So just let me know if you were able to do this. We can just put it on the side here. And the component, that is the physical model, which you can see at the back end, you can rotate it as you work it on CATIA. And in the exact same mouse commands, you can rotate it and pan it based on however you require. And if you hit on replay animation, okay, no, sorry. Yeah. So if you can see, the bottom is where my animations are. So if I'll hit play, you can see the robot arm moving. So this is since it's a predefined example and for a given amount of time, if you hit this play button in the bottom, you can see the model being moving in a certain way. So I'll just take it here. I'll remove my tree. And now you can see the animation of the model. So all of these components that you're seeing are built out of the Modelica library itself. So these are all the multi-body libraries. So multi-body package has basically this benefit of actually giving a 3D representation in the end. So using the body box, the revolute joints you have defined, you can actually have a whole robot model that you can build out of it. And then again, you have your simulation part, wherein you can go and select any of these variables and just double click it on in order for them to be plotted in a graph. So for example, if I'll go into mechanics, or okay, I'll go into control bus, and I'll just double click it here. So I'll have a graph that comes for this particular variable which is there. Now this I think is motion reference. So you'll have a motion reference graph that is created here. So any graph that you want based out of the variables that it has, you can plot a graph there. So this is one way where Modelica is quite helpful. Now what we'll be mainly doing is we'll be building a motor model. Not the motor model which you saw in the example here, but a little bit less simpler, not that complex, but a simpler model of a motor is what we'll be building. But before we move on to that, if anybody has any doubts, you can put it on the chat box and I can help you with that. Now to close this instance, what you can do is just close it from here and you can close your given model. Okay, so I'll just quickly check the chat box if anybody has any doubts. Okay, it's showing invalid compiler path error. Okay, so compiler path when you simulated it or when? Or anybody like Vineet and Praneet, you all have the same doubts. So when you simulated the model, it did not simulate, you mean? Okay, so after the simulation, you were getting an error. Okay. Okay, the compiler hasn't been installed, right? Lloyd, sir, are you there on the call? Meeting? Yeah, I think they are facing a compiler issue, so I'm not sure if they have Visual Basic installed for them or not. Since behavior modeling will need VB at the back end, I'm not sure if they have it for the compiler.
Compiler one, I need to check with Ashish.
Okay, but
For
I
time
think
being, just show them the process. Let's
right.
post the answer in the community.
Okay, no problem.
Yeah.
Okay, so I'll just show you process of building an electric motor model. You can just have a look at it. You don't need to work on it. Maybe you can build the component, but the simulation process won't occur at your end since you do not have the compiler installed. But you can maybe build the model side by side, or you can just have a look at my screen and I'll show you the process to build the motor model. Okay, so starting with how do we do is, so there's something we need to build a package first. Now, since we are building a model itself, we have to build a package now. So what we do is we go into behavior authoring, and then you can select out of the given options. So you have new Modelica class, new Modelica library, import a Modelica file, and import FMU. So what we'll be mainly using is new Modelica class. So you can just select new Modelica class, and now this is how the pop-up will appear. Now we'll rename the class as drive library. We'll just rename it as drive library, so lib is enough. Now what we want to do is we want to create a package first, and inside a package we'll have a model. So if you see the hierarchy, package is at the top, and then inside a package you'll have a model. So what you'll do is you'll just drop down, use this drop down and create a package here. So you can select package, and since there's nothing you want to insert it into and neither extend, so partial and extend are basically extending it from a given existing library itself or an existing template that you have. So if you have already a pre-built template, you can just extend it with it and you'll have all the components directly being formed in the new model which you create. So in our case, we do not want to do that. We have just renamed it to drive library and we have created a package and we can just do OK. So now you see it will appear on your main window itself. And now what we want to do is we want to build a motor model inside the drive library package. So again, what we'll do is we'll go into new Modelica class, but this time we'll select a model and insert, we will make sure that we select the class as drive library. So if it's already selected, you can let it be. If there's a different package that is selected, you can use this erase command. So you can erase it and go and select it directly from the tree itself. You'll just have to click on select a class and select it from the tree. And you can rename it as motor. Basically what we're doing here is we are creating a motor model inside a drive library package. So the package will be consisting of all the models that we are going to create. And you can press OK. Now you see there is the model which is created inside the package. So if you can see the line as well, it's inside the given package for the drive library. So now that we have our motor model set up, let's try to build it. So what we'll be making it with is the standard components from the Modelica library. Now we want to start with a few electrical components. So to name a few, we'll be needing a resistor, we'll be needing an inductor, we'll be needing a capacitor. So how do we get them? We just go into Modelica, we'll just close our mechanics library, and then since these components are to be situated obviously in the electrical package, because a resistor, inductor, and capacitor are electrical components, you can just go into the electrical package. And now there is multiple versions. So you have digital batteries, machines, polyphase. So you have a lot of components there. But these, so for the initial times, a user might get confused as to where to locate a given component. For that, they can use the search bar and search the resistor, and they can find it. But once you have a little bit experience with the DYMOLA tool itself, you don't really need to go and search it. All you can do is just enter a given package and then find it. So in our case, we need a resistor, so we'll go into analog, and in analog, we'll enter basic. So basic will be consisting of all the basic components that we require. That is the base level components. Like resistor is a base level component. There's nothing further to a resistor. It's resistor. After resistor, there's nothing. The resistor is built out of. You don't have those things. So what you can see is a resistor here. So all you need to do is click on it and select it like this and drag it and drop it on your edit window. So you can drop it out too. There's no issue with that. It's just that to keep it a little bit clean and not messy, we have this gray window which is up here. So you can increase the size of it too. So that's an option. But yeah, the first component which we needed is a resistor. Now that we have to define the properties of a resistor, we'll just double click it. So this window will appear. Now what you can do is you can rename the resistor to R. And now we'll give a resistance value to it. So the resistance value we'll assign is 0.5. And if you want to change the unit, so you can see ohms is a unit, and you can click on it and enter a different unit too. So you can go into kilo ohm, milli ohm, mega ohm, giga ohm. So depending on what you want to define there, you can define it. Also, you can define the alpha and the temperature reference values, but in our case, we are not entering into them. We let it stay like that. Now, again, if you want to know about the resistor model itself as to what all these parameters are, there's an info button here. So what you can do is just click on info, and you'll see a window that pops up. So the window basically consists of a little bit explanation about the resistor component and how this component is built out of, and the resistance, the values that you need to enter inside it. So if it's the Tref, it's the fixed temperature. If you use the heat port, and if you have the boolean, you set it to false. You have the temperature coefficient, the alpha value. So a little bit explanation can be gained from here. So we'll just press OK since we have just renamed our component and given in a resistance value. The next component that we'll be requiring is an inductor. Again, an inductor is a basic component, so you'll just drag it and drop it on your main window. So you have it like this. And now you can just double click on the inductor. You can rename the value to L, and you can just give in, okay, we'll just rename it to LA. Yeah. The inductance value which we're going to give is 0.05. We just rename it our resistance to also RA. And the next component that we'll be requiring is the EMF component. Before that, we also need the ground, so we just have a ground component that is present here. Now the EMF component will be present here itself, so you'll just have to search here. So we have the rotational EMF component. So again, you'll just need to drag and drop it onto your edit window. So you can see the EMF requires a value of K, which is transformation constant. And if you go into info, it will give you a basic description about what the EMF is and what this component can be used for and what it is built out of. This is what the EMF component is. First, we'll drag and drop all of these components, then we'll be creating and establishing the connection between them. Now we need a signal voltage, which is an input to it. So we are inside analog itself, and then there's a component called sources. So you just have to enter sources, and in sources you can go and search for signal voltage. So it's the first component itself. So you can just drag it and drop it onto your window, which will be the signal voltage component. Okay. Now, since we also want to apply a load, or through the inductor we want to connect a shaft, for that we'll be using a mechanical component. Since the shaft cannot be an electrical component, it needs to be present in the mechanical library. So what we'll quickly do is we'll just close our electrical library, electrical package, scroll down a little, and you can see there's a mechanics library. So you can just open it. And now, since the shaft will be a rotational component, you can enter the rotational package, go into components, and you can see there's something called as inertia. So this is the component which we require. So we'll just drag it and drop it onto our main window. So once you have the inertia component, let's rename it to JM and give it an inertia value of 0.001. So we have our inertia module set up. And there's just two more components that are left. Now the first, we'll be needing an interface. So an interface is basically if you're trying to connect multidisciplinary components. In that case, you'll be needing an interface component. So that is where, so since we need a mechanical interface, we'll just have to go into interfaces for rotational. And the component which we'll be requiring is flange B. So you can just drag it and drop it anywhere in the screen. And let's close all of it. Now we also need an input component. So the input will be, basically an input signal that we provide to our motor. And this input component will be present in blocks. So inside Modelica and blocks, if you go in there, you'll see multiple packages here again too. But what we need is again interfaces. And you can see there's a real input component here. So all you need to do is just drag and drop it onto your main screen. Okay, so let's quickly close all of it. And now I'll take you through the process of connecting these components and how the connections can be built. Now the first thing we'll be connecting is the resistor with the inductor. Now there are two ways in which you can do the connection. Now you can press on this small box which is here. You can just click on it and drag your mouse to the other component. So you see there is a connection that is built. If you double click on the connection, okay, it does not pop up in here. Okay, no problem. So this is how you can build the connection one way. So you'll have to drag it and you can create the connection by creating a contact there. But there's a much more simpler way that you could use, but I'll just replicate the process again. You just need to use the small box, click your mouse and drag your mouse towards the other component. So you'll have this dotted line that is created into a connection. Now the simpler method is basically click on your component, drag the component to the other component and just attach it. So you saw that green bubble that appeared. So the green bubble basically shows the contact has been established and you can bring it back to its original place. So this is a much more simpler way of creating a contact. I'll show you the process again. Just click on the component, drag it to the other component, wait till the green bubble appears and drag it back to its original place. So that's how simple it is to create a connection. So let's quickly build these connections for other components too. So for EMS, we need to create a contact between the inductor and the EMF component. So the blue box which you see, you can get a little bit detailed explanation here. The dark blue box is the positive electrical pin for the component, and the light blue one is the negative pin. So if you just hover over it, you can see the negative pin is there, and for the dark blue one is the positive pin. That's how they differentiate between the positive and negative pins. So if you want to reorient a given connection, you can just click on it and you'll have these handles that appear. So you can just click and drag it and orient it in a certain way. Now we need to create a connection between the ground and the EMF. So all you have to do is just drag the ground component and create a connection like this. So we have our EMF and ground. Now one more thing which you could do is, if your component, since if we try to build a connection right now with the voltage, signal voltage and the ground, it looks a little bit weird, mainly because, so for example, I'll just create it. It'll be like this. So this is how we want to create a connection, but if you can see, it just looks a little bit different. I mean, I want the component to be turned around. So what I can do is I'll just delete these connections. I'll just click on my voltage model. And if you can see this command can be used to rotate the component in a given way which you want. So right now what I want to do is I want to flip it by 90 degrees. So I can use maybe rotate 90 degrees. Okay, so I have it rotated 90 degrees. And next what I want to do is, so I can either have this end towards, so you can orient it any way you want. So you can maybe vertically flip it, or you can horizontally flip it. So there's a lot of options which you could use. But in our case, we want the orientation to be something like this, with the negative pin upwards and the positive pin downwards. So once you have by using those commands, once you have achieved this, what you can do is just create a connection. And similarly for the other end too. So this is how you'll be creating the connections. Okay. So once you have done this, you have to connect the resistor to the inductor. You need to connect the inductor to the EMF, the positive and negative. Similarly for the negative pin and the positive pin, the ground. And then similarly for the voltage signal. Now the input block which you have needs to be connected with your voltage signal, since this is what will act as an external input. So if you need to give an external input to your motor model, you'll need an input connector block. So you can just drag it to the component and you see the green bubble that appears, and bring it back to its original place. So this is how you create a connection between them. Similarly, right now if you can see, this EMF is an electrical component. So it has a negative pin, a positive pin, but it also has a flange here. So this is a flange B component. Now if you try to connect this mechanical component, that is the inertia component, with an electrical pin, that is an electrical connector, the connection won't establish. So I'll just show you. So you'll see a red block appears and it shows incompatible connectors. So you cannot connect two components of difference. So a mechanical component cannot be connected to an electrical component unless there is a flange which it has, or a shaft which it has. So in this case, the EMS has a shaft which it has. So we'll just drag and create a connection between them. So between the flanges, there is a connection that is created. Now similarly, this flange component, also a connection needs to be established, and this is how it will look like. So this is basically our internal model structure which we wanted to achieve. So I'll just quickly orient it a little differently. Okay, no problem. Yeah. So once you have this, so now if you see, what I'll do is, since we have to test this motor too, okay, so we'll create a new class again. So we'll go into this, or the new Modelica class. We'll rename a class as test motor. That's basically we're creating in order to test our motor if it's working fine or not. Now we need to insert it in drive library. So the package is where you'll be inserting all your models into. And once you click OK, you have the test motor here. Now what you'll be doing is, you can drag and drop this motor onto your screen itself. So what we did initially was, we created a motor model using the components from the standard library. But now what we have done is we have created a motor model itself. But now if you see, the motor model is very vague for somebody to understand. I mean, it's just written motor and you have an input and output. There's no much understanding to it. So this is where the icon layer comes into picture. So I'll just show you what an icon layer is. So we'll just go back to our motor model. And if you just scroll towards the right side, you'll see something called as an icon layer. So it basically switches between the diagram layer and icon layer. So diagram layer is what we are seeing right now. One second. And icon layer will be the model of how it looks for you. So you can just switch it from here. So now you can see it has changed the UI. So this is your icon layer now. So now we can create an icon for this given component. So what we'll do is we'll maybe create a rectangle now. So we'll just try to build something that looks like a motor so that it can be better for the understanding itself. And then we'll use a polygon maybe. So the ones who are trying to replicate it with me, you can follow this process and replicate it the way I'm doing it. So you can, any kind of shape is, any kind of shape could be fine, anything that you can build. Something that makes anybody else understand what you're trying to build or what you're trying to achieve is what is important here. Okay. So once you have this, we'll create one more small rectangle that shows a connection here. So any shape that you want, you can create it. There's no restriction to it. Now the last thing we want to signify is a line here. That's it. Just showcase that. Yeah. So now we just put in some color to it. So you can just go onto the left side and pin this particular window. So it automatically opens up. If it is already pinned, you can use it. If it's not, you can just go onto the side and just pin this window. Now let's select a rectangle. Now we'll enter some color into it. So we'll just use fill color and we'll select black. And the fill style, you'll have to enter solid. So once you do it, you'll have a given this thing there. Okay, we'll just change it to maybe red. Yeah, this looks better. Now for the below component, what you have, you can just select black here and again select solid. So you'll have this. And for this here, what we can do is we can maybe select gray and select solid. So it looks something like this. And now we can, the Modelica graphics property, we can just pin it, we can just unpin it. And we can change our layer right now. So we'll just go back to our diagram layer. Okay, so nothing has changed here. But if I go into test motor, and now if I drag and drop my motor model, so what you can see is the model which we built now. So this could be a little bit helpful in order for the user to understand, or if you're collaborating with somebody or a customer that you're working on a project for, it could be helpful for the customer to understand actually what exactly you have built basically. So this is the motor model which we built right now. Now let's try to test it out. So I'll just quickly replicate the process again and tell you what we just did. So we went on to icon layer, created a diagram for the given motor model. We switched it back and dragged and dropped the motor model to our main window. Now what we want to do is we want to try and analyze this particular motor model. So we'll just go into motor and we'll go into blocks and source this. So you can maybe just take in a step signal. So this is basically an input signal that will act, and you can create a connection between them. And now we can go on to simulation and you can set up a simulation setup. So let's keep it to 4 seconds. So you can change the integration, that is 500 seconds, or change the algorithm to anything else that you want. We'll keep it to DASSL and the tolerance is 0.01. So you have various things that you can play around with while setting up the simulation. and accordingly you will have your results displayed there. So once you do that, then you can hit on simulate, and then if there are any errors, then that will be displayed. But if they aren't, then you'll have your model being simulated. So once you have your simulation completed, you will have something that looks like this. So you have 13 messages reported, but if there are no errors, the messages will be hidden itself. Now, if you want to plot anything out of these graphs, what you can do is just go into motor maybe and enter your flange component, and there is a phi value. You can just double click it and you'll see your graph here. You can maybe plot the tau component. So there's anything you can plot here basically. Then you have your step signal. So the step signal is what we have given in right now. So we haven't defined any value, but the input basic which it takes is that height is 1 and is what it takes, the step signal. So this is how you can simulate a model and create a model on DYMOLA. Now what we'll do is we'll actually try to create a whole motor setup itself. So what we did right now was just create a basic motor. But now what we can do is we can also create a whole motor setup, that is a test motor bench itself, which has a lot of components attached to this given motor model itself. Okay, so I'll quickly take you through that process of building it. So we'll close this. And now we'll go into behavior authoring. Behavior authoring is where you create a new class. And now the class which we'll be creating is motor drive. One more thing while naming the component you need to make sure is if you give just a space between them, you can see the symbol here turns red. That means you cannot give a name like this. You'll have to either give an underscore or use camel case. Camel case is basically where your first letter of your words are capitalized. So you can either give motor drive like this or just enter an underscore here. And make sure you enter it into your drive class, because if you don't, it will be just created as a new model without any package. So we'll insert it in drive library and select OK. So you have your motor drive component here. Now we'll drag and drop the motor component again. We'll just increase its size a little. Yeah, now we'll keep it here. Now the other components that we'll be requiring are basically feedback. So we'll go into math, which is basically in blocks. So we'll have to go into Modelica blocks. And you see there's a math package here, and go into feedback. So you can just drag and drop this component here. The next you'll be needing is a PID controller. So it's in blocks itself, but this time you'll have to enter continuous. So there's a PID controller which you can take in. Then you'll be needing a gearbox, since the motor shaft will be connected to a gearbox to step down the value. So you will need a gearbox component. The gearbox will be present in the mechanics package. So you'll just have to scroll down, enter mechanics, rotational, components, and you can see there are multiple gearboxes. So there's a loosey gear, there's an ideal gear. So what we'll be requiring is an ideal gear. And we'll also be requiring an inertia component again. So we'll just drag and drop the inertia component. Yeah. So one thing, we'll also given a few values. For the gate ratio, we'll given the gate ratio value is 100. It's basically transition flange A5 to flange B5. And similarly for the inertia value, we'll given J value as 10. So we'll just rename it to J and given a value of 10. Okay. Now we'll also be requiring an angle sensor. So the angle sensor will be present in the mechanics library itself. So you'll have to just go into sensors and angle sensor. So just drag and drop it onto your screen. And we'll also take in a step value now. So we'll go into sources and step. Okay. Now we'll create a connection between all of them in order to build a whole motor drive itself as to how it will look. So the step will be basically acting as an input signal, so we can keep it at the outside itself. Now the other thing that we have to do is we have the motor model and the gear. Now the inertia component will act as a feedback. So the angle sensor will act as a feedback for the input. Will be the input for the feedback block here. So we'll just rotate our component now. Okay, not like this. Yeah. And we'll orient this. Yeah. So this is how we would want our angle sensor to be oriented. And we'll connect the flange of the angle sensor with the flange of the inertia component. Similarly, for the gear and the inertia block, we can create a connection. And now we'll create a connection between the motor component and the idle gear. Since the motor is directly connected with the idle gear, we'll just create a connection there. The next connection you'll have to create is between the PID controller and the motor model itself. So you can just create a connection here. And similarly for the PID and motor. Now the feedback will take this as the input, that is your angle sensor. And the input for the feedback will be coming from here. So what we're trying to do here is based on the output that is achieved in the motor and the value that the angle sensor measures is what is given as a feedback, and accordingly the rotation will be changed. That is what the objective here is basically. So this is how we'll be building the circuit, and we'll just rename we'll just rename it to controller. And we'll change our simulation setup a little. We'll simulate it for 5 seconds. We'll let the number of intervals be 500, and we'll let the algorithm be the same. And you can hit simulate now. So as you see, there's no errors that are generated. So we'll try to plot a few graphs here. So what you're trying to plot is the step Y. And for the motor component, we'll be, where is it? Motor. Okay. Yeah, no problem. So basically you can plot any of the graphs from here, and based on the change in values for the PID controller, so you can actually change a few values for the controller itself, and then accordingly you can plot any graphs. So in this example, basically this is how you build a motor model, and then you can validate your motor model using the simulation while doing the simulation. So you can plot any of these graphs and accordingly validate your motor model. So this is for motor, but you have many more components that you could build. So I'll just show you one or two more. Enter into example. And if you go into, okay, so I'll show you an engine model which is built here using the loops. Yeah. So if you see this is how you can build an engine model. So this, if you see, so for a mechanics type of a component, you'll need a world library as an input. And then we have multiple engine cylinders here. And if you do a show component for them, you can see as to how these engine models are built. So they have a lot of body box, a lot of joints that are associated, the connecting rod that is present. So a lot of definitions in that way are given. And these are little complex simulations, but if you simulate it, you can actually see a simulation of a V engine itself, a V6 engine. So we'll just let it simulate. It will take some time, these models, since they have a physical product also at the back end. If you play it now, just slowly speed down. It's quite fast. Let's do it. can see, this is how rotate it here. This is how a V engine can be modeled. So there's a lot you can do with these components and from the libraries that you have, the standard Modelica library. So there's only one more example that we're going to try now, is to try and build a fluid circuit. So I'll quickly show you how to do that too. So before that, what the Modelica fluid library helps in doing is building one-dimensional fluid circuits. So you can drag and drop components from the fluid libraries in order to build these fluid circuits. So the mediums which you'll be defining are so the media library is present from where you can define the mediums, or you can define your own medium properties if you have the fluid properties that you want to define. Okay. So coming on to what the fluid library consists of, it basically has vessels, pipes, it has machines such as pumps and then you have valves, you have sources, and you have the sensor components too, such as temperature sensor, fluid sensor. So all of these components are also present there. Now, how do we build is, we'll again build a new Modelica class. We'll build a package, and we'll build a MSL package, or we can directly build a fluid package. So you do not want to insert it into anything. We want to create a separate package. So we have a fluid package here. And now we'll create a model which is valve liquid. The model which we're trying to build here, so we have basically two source, a source and a sink, and a common vessel in the middle. And you have two valves. So these valves are operated at different timings, and accordingly the amount of fluid will be flowing through the source to the sink, and that is what we are trying to simulate here. So we'll insert it into fluid package, click on OK. Now we'll try to build the component itself. So I'll show you the process of how to build that. You can either replicate the process, or you can just have a view of, you can just look at my screen and I'll show you how to build this given component. So what you can do is, you can enter the fluid library now. So there's a fluid library just below the mechanics library. And inside fluid, you can go into sources. So you have a fixed boundary component here. You can just drag and drop it onto your screen, and you can present it here. Now, if you want to understand what this is, you can use the documentation info command. So it's basically a fixed boundary, that boundary pressure or boundary density, boundary temperature. So you can define all of these values. And it's basically acts as a source for us. So we'll just rename this to source. Now we can fill in a medium property. So the medium is basically the type of fluid that will be flowing through them. So there's a lot of options from which you could choose from. What we'll be choosing is the we'll be choosing 1,2-propyl glycol, 47% mixture with water is the component that we'll be choosing. And we'll be giving the pressure input to it. So it's a 10 bar, it's a fluid which is a 10 bar pressure, and the initial temperature is 21.85 degrees Celsius. Now again, the Celsius is it's already selected the unit for temperature, and similarly for pressure you have all of these, but in our case we need 10 bar pressure. And the rest of it you do not need to provide an input to. So you can just press OK. So you have your source component here. Next, we'll be requiring a valve. So you can just go into valve and use valve incompressible. So just drag and drop it onto your screen and double click it. So we'll have to give in a fluid medium for it. So the medium across all the components needs to be the same. You cannot have different fluid mediums defined. All of the components will have the same fluid medium across them. Now the next thing you'll have to define is the pressure. So this will be the nominal pressure drop that will be occurring in the first valve. Then you can give in the flow rate to the valves that you have. So we're giving it as 1.2 kg per second. And we'll also give it the density of the inlet. So we'll select kg per meter cube and we'll give it 1000. So the nominal inlet density. And we can press OK. So we've defined a valve variables too. The next what we'll be requiring is we'll go into vessels, and vessel basically has a closed volume. So this is basically acts as a place where you can fill in liquid and take out liquid from. So we'll just place it here. We'll again go inside it, select the medium which we have. It's 1,2-propyl glycol, and use sports data. We'll set this to false. We do not want any of this, so we want to neglect the pressure loss and the kinetic energy inside the tank itself. Now the volume of the tank, we can define it to 0.03 meter cube. And similarly on this side, we'll again need a valve. So basically what we are doing is, from the source, we have a valve that operates on a given input, and the fluid enters into the volume component. And again, there is a valve on the other end that basically has an input again through which the fluid will be flowing out. So let's place it here and fill in the details for it. So the medium, we'll again select it to 1,2-propylene glycol. And you can just give in the pressure values here too. So the pressure value here, the pressure drop to the second valve is going to be 4. The flow rate is going to be 2 kgs per second, and again the density is going to remain the same, which is 1000. And the last component which we'll be requiring is the sink. So we have again, where is it? Yeah, sources, fixed boundary. You can just drag and drop it here. So this will act as our sink. We just rename it as sink. We'll select the medium to 1,2-ethylene glycol. Yeah. The pressure value which we'll be giving in for the sink is 1 bar, and the boundary temperature is 21.85 degrees Celsius itself. And we'll also flip this component. So now we'll create a few connections here. So the first is between the valve and the sink component. Then we have between the volume and the valve. Then this particular volume and this valve, which will be acting as an output to the volume. And then between the sink and this particular valve. So the fluid will start flowing from the source. Once this valve opens, will enter the volume, and from the volume component, it will flow out of it by this particular valve into the sink. Now, since we also want these two valves to be opening at 2 different timings, so for that we'll give it an input signal as to when these valves need to open. So we'll go into sources, and in sources there's a ramp signal. So we'll just drag and drop it here. We'll give it a few values. The height will be minus 0. You can see the image which is there on the right, which actually shows what the height means. So height is basically this. The duration for which the valve will be open will be for 2 seconds. The offset will be 1 second, and the start time will be 1 second. So basically this is how, so it will be open for 2 seconds, and the height is minus 0.99, and this is how you will be defining the values. So this is for closing valve V1. And we'll again copy paste it. So we need one more signal like this. So we can just copy and paste it. And we just connect it here with this input signal of the valve. Now the valve V2, we just need to do one change, that instead of 2 seconds, it's open for only 1 second. And that's it. So one thing we need to make sure is, if you're trying to build a fluid circuit, you need a system component. So the system component is basically what defines the ambient values and the ambient temperature and ambient pressure. So the systems component is important in order for a fluid simulation to run. So this is one important thing that you will have to take care of. So now that we have built the circuit, we can simulate it. So we'll go into simulation, set up a simulation scenario. So we'll get around 4 seconds, and we'll let the remaining values stay the same, and we'll go and simulate the values. Now what we can do is, we can validate all of this data using our graphs itself on the behavior modeling platform. So I'll just plot a few graphs and you can see what exactly the simulation will look like. So I'll just select MB flow. Since we need to plot 4 graphs, I'll just shorten the size of this. The other one which we'll be requiring is close V1, that is when the V1 valve opens. Then we'll go into volume and we'll go into medium. And the pressure drop that occurs in it. And the last one we'll be requiring is the way the V2 valve works. Okay. So what you can see here is basically the flow. So at 1 second, the valve V1, so this is the volume component. So at 1 second, basically both of these, okay. So at time equal to 1 second, V1 and V2 valves close in 1 second and they both have difference flow. So you can see that the valve V1 is open for a time duration of 2 seconds, that is from 1 to 3 seconds. On the other hand, the valve V2 is open only for 1 second. That is how we define a ramp signals are. And the fluid flow is something like this, and this is what the pressure drop looks like. And the volume flow occurring in the component itself is something that looks like this. So you can use this measure component and see how the fluid, so initially the fluid rises, and then once the valve opens, it flows into the volume component. That is, once the first valve opens, flows inside it, and at the same time the other valve also opens at 2 seconds and this volume starts flowing out of the system. So this is how one of the fluid circuits can be simulated. So I'll just show you an example apart from this as to what other things can be achieved. So you have pumping system, heating systems. There's a heat exchanger model. So you could just double click it and see how the heat exchanger model is built. So it has a pipe. You can give in 2 different fluids, a primary and a secondary, and the heat exchange could happen between them. So there's a lot more you could do with the fluids libraries and as such with the other Modelica standard libraries itself. So since you could not really simulate, I'm sure there might be a few doubts for you. It was mainly related to the compiler issue, since you need a backend compiler at your end in order to simulate these models. But that being said, I mean, you can try and model these components in order to build a circuit. You can try and understand these examples which are present on the Modelica standard library itself in order to build a given system out of the standard components here. So if there are any doubts that you have, you can post it on the comment section and I could help you out with that. But that's mainly it on regards to the DYMOLA part. So this was the electric model DC motor that we built, and DC motor consists of these components that we built from the Modelica standard library. Similarly, this is the Modelica fluid library and what all it consists of. That's it from our end on 1D simulation. If you have any doubts, you can post it on the comment section. Yeah, Lloyd sir, are you there on the call?
Hi, Siddharth. I'm there in the
Yeah,
call.
hi. Yes, that's
Hello.
it on the, yeah. Did somebody?
So
Hello.
you can check if they have any questions with you. Yeah.
Yeah, I'm just taking a look at it.
Hello.
I'm not yeah.
Mr. Siddharth,
Oh, yeah, that Mahendra, yeah.
I think that it's a long session. So if you wish, you can take a break for 5 minutes. As since
Right.
2:30, it's a long session.
Right.
Mm.
I mean, anything is fine by me because that is what we had from our end. So,
Yes.
Lloyd sir, do we like anything that we need to do, or do we take a break?
I'm just building on a survey. We'll take
Okay.
some 10 minutes break. We'll connect back at 4:15, and then we'll have the survey done, and then we can close up the session.
Sure, that can be done too. Yeah.
All right.
Sure, we can
Dharmendra,
take a break then. Yeah.
Dharmendra, you there?
Yes, yes, yes. Okay.
Okay, we will connect back at 4:15, and we will have a survey done, and then we are good to close the session.
To whom? To whom?
We need to get a survey done on the 3D Experience platform. We are just publishing a form. We will fill that around 4:15. We will show the students which form that is that they need to fill. And
Yes.
once that is done, maybe 5-10 minutes they will spend on that. And 4:30, no, we will log out from the session.
Okay. Okay.
Yeah. All right. Thank you.
Okay.
Okay. Hi everyone. Is everyone back? Students, if you can, just type yes or no, it will be great to know if you are there in the session. All right. So thank you so much, interns, for patiently listening to us from last 2 days. That is on Friday and Monday. I hope the sessions were fruitful, and thank you so much, Mr. Ashish, Saurav, and Siddharth, who are my colleagues, who kind of spared their time to kind of get you trained. So thank you so much for all your efforts. And also, we would like to thank IIT Rupert team for giving us this opportunity to present our solutions, and for this project purpose. So, before we say bye to you all, we have a small survey posted in the 3D Experience community. In the swim community, we would like you, all of you, to kind of give spare some 5 minutes and do that survey. So, if Professor Dheeraj is there, we would like to have some few words with you, sir.
Thank you,
Actually,
Mr. Siddharth, Mr. Lloyd, and Mr. Saurav for such a wonderful session and for your valuable time for guiding our interns more about the software. Thank you so much, sir.
Welcome, Miss Amy.
Give me a few minutes. Let me ask sir if you join me.
Okay, in the meantime, what I will do is, I'll just, if somebody makes me the presenter, I would like to show this which survey to you all.
Yes, sir. I'm making you presenter.
All right.
done. You are now presenter, Mr. Lloyd.
All right. I can share my screen. Okay. Can you all see my screen?
Oh, yes, your screen is.
All right. So let's just go to our IITR platform. So guys, I remember, I think you still remember how to access the communities. In case if you don't know how to access the communities, just go to this section over here from the platform, click on communities and extend the tab. Okay. And then you will find the IIT Roper community over here. You can just click on that. And just now, Saurav has kind of published a survey. We can just say answer, and then survey will be open. You can just start with your name, and just it's very simple, straightforward survey. If you can, it would be really great if you all can spare some 5 minutes and give your honest opinion about the sessions. So, do we have Dr. Dheeraj in the session?
Sir, because of some technical issue, he was not able to connect to the internet. So he said we can close the session if we are good to do go, and he will later on contact you.
All right, ma'am. Thank you so much. So this is all we wanted to tell. So thank you all students so much for listening to us very patiently. We will, please make sure you use this platform for your project needs. And uh, you know, there might only the top 100 might make out to the real competition. So I would love to see you all the 100 interacting in the platforms and competing against each other. Okay. So good luck to all of you.
So interns, we will meet at 5:30. Till then, you can take a break.
So now we can wind up the session, and thank you, Mr. Siddharth and Mr. Lloyd, for connecting with us. So I am now just wind up the session.
Dharmender sir, no, just stop the, or we can wind up.
Okay,
We can rejoin at 5:30.
I
Dr.
can
Dheeraj sir will
just stopping it, and I am stopping the live
live
YouTube live,
streaming,
and
right?